Welcome to Chemistry Lover, and today in this video I am going to discuss about one of the very famous organic chemical reaction, and which is none other than Fischer indole synthesis. This is a standard heterocyclic synthesis reaction and it is done by none other than the great Emil Fischer, and it is one of my favorite reaction for its mechanism and for its beauty. So in this video I will discuss the mechanism and what are the effect of the reagent on this particular reaction. So stay with me, let's start today's topic. So this is the Fischer indole synthesis. As you can see, it starts with one aromatic hydrazine. In this case it is phenyl hydrazine along with a ketone, and these two reagents, when they are treated with catalytic amount of acid, you will get this indole product. Now we will look into the mechanism of this particular reaction. So if we talk about the mechanism of this reaction, the first step which you can easily recognize is the formation of the imine, because whenever you treat any amine, normal amine, with a ketone, it always generates a imine or Schiff space. So in this reaction also you will have a Schiff space or imine. So this is the first step of the reaction where you will get an imine, right? Now between these two nitrogen, you can definitely understand that this nitrogen will be more nucleophilic, because this nitrogen lone pair is delocalized into the phenyl ring. At the same time, you can see sterically it is also free. So these two reasons makes this nitrogen more nucleophile, and that's why this nitrogen takes part in this Schiff space formation. Now what is the next step? So you know that imines are inherently less stable, so they will readily undergo the tautomerization to give you this thing, and this is a type of enamine. You can see this is a type of enamine, right? And you know that enamine are more stable than imine, because this carbon-carbon double bond is more stable, or it is kinetically more stable. So this is the case. Now, so from that you can also understand that to undergo Fischer indole type reaction, your ketone substrate that needs one alpha hydrogen, because otherwise this tautomerization cannot take place. So this alpha hydrogen is a necessity for this Fischer indole synthesis. Now if we open up this structure, you can see, so here you have one hydrogen, here you have another nitrogen, and now we will open up the structure of this phenyl ring. So if you open up, you can see there you have a double bond. And now if you recall one famous pericyclic reaction, which is 3,3 sigma tropic rearrangement, so you can label this is 1, 2, 3, and this is 1, 2, 3. So this particular reagent is perfectly oriented for a 3,3 sigma tropic rearrangement. So this is how we can show it, and it will undergo a 3,3 sigma tropic rearrangement to give you this NH over here. Here you will have one hydrogen. So you can see this phenyl ring, it loses its aromaticity, and here you will have this NH and this. So this again, this imine is formed here. Now if this hydrogen goes here, it can regenerate its aromaticity to give you this. So here you have this NH, and here you will have this aniline moiety. So this is basically aniline group. Now what next can happen? So you can think this particular group as a carbonyl type functional group, because this particular center is electrophilic and this nitrogen has a lone pair, so it will readily attack over here, and that will give you one intermediate like this. So here you will have this one hydrogen over here, one NH over here, and if you recall, we did the reaction, or we showed that the reaction we are doing in acidic medium. So here you will have a protonation, so you will have NH2 over here, right? Now further, as you are doing the reaction in acidic medium, so this can be protonated again to form NH3 plus, and then if this nitrogen lone pair push, this can go as ammonia. So here what you will get, you will get this intermediate. So here you have NH, here you will have this plus, right? And now to neutralize this charge, what will happen next? So here you have one hydrogen, so this hydrogen can go, and this is how this charge can be neutralized. So here you will have this NH and this, so this is the indole moiety. So this is how we get the indole. So this is the standard mechanism of the Fischer indole synthesis, and you can see this reaction involved a lot of reactions. For example, in the first step it is the formation of the enamine, then the tautomerization to form the the first step it forms the imine, then the formation of enamine through tautomerization, and the in between, the which step is more important is the 3,3 sigma tropic rearrangement. So you have to remember that step, and then again the standard electrophilic attack on the imine moiety. So I hope that this mechanism seems easy to you. Now let us discuss the regioselectivity of this reaction, or the regioselectivity of this particular synthesis. For example, in this case, so here we used the NH2, this compound we use. So we can use the same compound, but in the previous case we used a symmetrical ketone, namely acetone. But what will happen if we use some unsymmetrical ketone like this, right, where you have two different type of alpha hydrogen atoms, right? Now of course, after the first step, all the things, so in the first step what will happen, so this enamine formation will take place like this, NHPH. This step is similar for the both. Now in the tautomerization step, either this hydrogen can go or this hydrogen can go, and depending on that you can have two situations. One is you can have enamine over this side, here you have NH, you have NHPH, so you can have enamine over this side, or you can have enamine over this side also. Now you can easily understand that whether the enamine or the double bond is forming over this side or this side, depending on that the structure of your product may differ. For example, let's say you have this enamine. So if you have this enamine, then you will have reaction from this side. Okay, so from here the 3,3 sigma tropic rearrangement will take place, and you will have, so I'm just skipping the initial steps. So you will have finally the NH2 group over here, this will aromatize back, and here you will have this thing, this NH and this, and then the attack will take place over here, and after few steps what you will get, you will get a product like this. So here you will have nitrogen, this and this. So this indole you will get from this. So we have seen that when the enolization takes place from this more substituted side, then we get this product, and this occurs in weak acidic medium, for example acetic acid. And now we will see when the enolization takes place from this less substituted side, what will happen. So this step is the 3,3 sigma tropic rearrangement, and after some of the steps, what you will get this NH over here. Here you have this, and here you will have this aniline moiety, right? And now this will attack over here, and after few steps, what you will get a product, this one. So here you will have substitution, here this and this NH. So this product you will get. So you can see, so it is for acetic acid, and now this product you can get. So now the question is when you will get this product and when you will get this product. So I already mentioned that when you use weak acid, for example acetic acid, you will get this product. Why? Because then the reaction is thermodynamically controlled, because it is in weak acidic medium, it takes longer time, and when you do reaction for longer time in weak condition, in milder condition, then reaction will follow the thermodynamically controlled pathway, which goes through more stable intermediate, less energy demanding pathway. You can see this double bond is more substituted, that's why it is less energy demanding and it is a thermodynamic product. But when you do the same reaction with same substrate but in high concentration of acid, for example concentrated H2SO4, very high concentration of acid, then you will get a mixture of this product. So you will get this product as well as this product. Why? And it will be almost 50-50 mixture. Why? Because then the reaction will not have any kind of selectivity, it will just a random reaction. The double bond, after the imine formation, the double bond will randomly form over this side as well as from this side, because there is no selectivity, and that's why you get the mixture of these two products. So whenever you have a question on this Fischer indole synthesis, you should always look for the condition, whether it is in weakly acidic medium or in a high concentration of acid. That is very important, and this is the reaction. And one thing you should note is that this reaction is a very wonderful reaction because its mechanism is very important. And one thing I already mentioned, that one ammonia molecule is removed in this reaction. So this question sometime they ask that what is the molecule that is excluded from this reaction. So it is ammonia. You can see in this step ammonia molecule is removed. So this is the mechanism of Fischer indole synthesis. I hope that I discussed all the important aspect of the reaction. Hope this video will help you. Thank you for watching, and if you didn't subscribe this channel yet, then subscribe now. Thank you for watching.